Polymers and composites derived from castor oil, synthesis, properties, and applications. The increasing demand for sustainable materials has accelerated the transition from petroleum-derived polymers to renewable alternatives. Among various bio-based feedstocks, castor oil has emerged as one of the most versatile and industrially relevant resources for polymer synthesis. Derived from the seeds of Ricinus communis, castor oil is a non-edible vegetable oil that is abundant, biodegradable, and environmentally benign. Its unique chemical structure, particularly the high content of ricinoleic acid, enables the formation of a broad spectrum of polymeric materials with tunable physicochemical properties. Consequently, castor oil-based polymers and their composites have gained considerable attention for applications ranging from coatings and adhesives to biomedical devices and structural materials. Composition of castor oil. Castor oil is typically extracted from castor beans through mechanical pressing or solvent extraction techniques. The oil is pale yellow, viscous, and non-volatile, and has been utilized historically for medicinal and industrial purposes. In modern applications, it serves as a raw material for the production of lubricants, coatings, cosmetics, surfactants, and pharmaceuticals. India dominates global production, contributing the majority of the world's castor seed supply. Chemically, castor oil is composed predominantly of ricinoleic acid, approximately 90%, with minor contributions from linoleic, oleic, palmitic, stearic, and linolenic acids. The distinctive feature of ricinoleic acid is the presence of three reactive functional groups: a hydroxyl group, a carbon-carbon double bond, and an ester linkage. These functionalities enable a wide range of chemical transformations, including esterification, amidation, hydrogenation, epoxidation, acetylation, and dehydration. This multifunctionality provides exceptional flexibility in designing polymer architectures such as polyesters, polyamides, polyethers, and interpenetrating polymer networks. The presence of a hydroxyl group in ricinoleic acid makes castor oil inherently suitable as a polyol, which is particularly advantageous for polyurethane synthesis. Unlike many other vegetable oils that require chemical modification to introduce hydroxyl functionality, castor oil can often be used directly. Additionally, the long aliphatic chain in ricinoleic acid contributes hydrophobicity and flexibility to the resulting polymers, influencing their mechanical and thermal behavior. These characteristics distinguish castor oil from other vegetable oils such as soybean or sunflower oil, making it a preferred candidate for bio-based polymer production. Castor oil-based polymers. Polymerization of castor oil derivatives generally proceeds via two principal mechanisms: polycondensation and polyaddition. Polycondensation involves reactions between functional groups such as hydroxyl and carboxyl groups, often accompanied by the elimination of small molecules like water. This approach is widely used for synthesizing polyesters and polyamides. In contrast, polyaddition reactions involve the addition of monomers containing unsaturated bonds without the formation of byproducts, as seen in polyurethane synthesis. The choice of polymerization route significantly influences the molecular weight, structure, and properties of the final material. Castor oil-derived polyurethanes. Among castor oil-derived polymers, polyurethanes represent the most extensively studied and commercially important class. Polyurethanes are formed through the reaction between polyols and isocyanates, producing urethane linkages. Castor oil serves as a natural polyol, and its hydroxyl groups participate directly in the polymerization process. By adjusting the ratio of reactants and the degree of cross-linking, materials ranging from soft elastomers to rigid thermosets can be produced. For instance, cross-linked polyurethanes synthesized using castor oil, glycerol, and diisocyanates exhibit excellent elasticity and biodegradability. The incorporation of glycerol enhances stiffness and homogeneity due to its compatibility with polar isocyanates. In another approach, amorphous polyurethanes prepared via transesterification of castor oil demonstrate low glass transition temperatures and good thermal stability, making them suitable for polymer electrolyte applications. Their flexibility facilitates ion transport, enabling measurable ionic conductivity when doped with lithium salts. Hydrophobic polyurethane films derived from castor oil and hexamethylene diisocyanate have also been developed, with water contact angles around 90 degrees, indicating significant resistance to moisture. The mechanical properties of these films can be tuned by varying the degree of cross-linking, making them potential candidates for biomedical scaffolds. Furthermore, Castor oil-based polyurethane foams have been synthesized using environmentally friendly processes involving glycerol and blowing agents such as water or cyclopentane. These foams exhibit low density, controlled cell morphology, and favorable thermal insulation properties, making them suitable for applications in construction, automotive, and aerospace industries. Advances in green chemistry have also enabled the development of thermoplastic polyurethanes with high thermal stability and good adhesive performance, particularly for wood bonding applications. Castor oil-based polyesters. Polyesters derived from castor oil represent another important class of bio-based polymers. These materials are typically synthesized through polycondensation or ring-opening polymerization. The latter method is often preferred due to its ability to produce high molecular weight polymers under mild conditions. The hydrophobic side chains of ricinoleic acid act as internal plasticizers, reducing the glass transition temperature and imparting flexibility. Castor oil-based polyesters synthesized using multifunctional monomers such as sebacic acid, citric acid, and polyols exhibit soft, elastomeric behavior. Surface properties, including wettability, play a crucial role in biomedical applications, as they influence cell adhesion and protein interactions. Castor oil-based polyamides. Polyamides derived from castor oil are economically attractive and widely used in engineering applications. Sebacic acid, obtained from castor oil, is a key monomer in the synthesis of various polyamides, including nylon variants. Polyamide synthesis can be achieved through the formation of ammonium salts followed by high-temperature dehydration or through aminolysis reactions. Advanced catalytic processes enable the production of amino esters from castor oil derivatives, facilitating the synthesis of polyamides with controlled structures. Recent developments include polyester amide vitrimers, which combine the properties of thermosets and thermoplastics. These materials exhibit dynamic covalent bonding, allowing them to be reprocessed and reshaped multiple times without significant loss of performance. Castor oil-based epoxy. Epoxy resins derived from castor oil offer a sustainable alternative to conventional petroleum-based epoxies. Epoxidation of the carbon-carbon double bonds in castor oil produces oxirane rings, which are highly reactive intermediates for polymer synthesis. These epoxidized oils are used in the formulation of biolubricants and as plasticizers in polymer systems such as polyvinyl chloride. For example, epoxidized acrylated castor oil has been shown to significantly reduce the glass transition temperature of PVC while improving flexibility and thermal stability. Hyperbranched epoxy systems synthesized from castor oil exhibit excellent toughness, flexibility, and mechanical strength, making them suitable for coatings and structural applications. While castor oil-based polymers offer numerous advantages, their properties may not always meet the stringent requirements of advanced applications. To address this limitation, significant research efforts have been directed toward the development of polymer composites. By incorporating fillers such as nanoparticles, natural fibers, and inorganic materials, the mechanical, thermal, and functional properties of the base polymers can be significantly enhanced. These composites are particularly attractive for applications requiring high strength-to-weight ratios, thermal stability, and specialized functionalities such as electrical conductivity or antimicrobial activity. Castor oil-based polymer composites. Polyurethane composites based on castor oil have been extensively investigated. The incorporation of titanium dioxide nanoparticles, for instance, enhances damping properties, making these materials suitable for vibration control in automotive and aerospace systems. The effectiveness of these composites depends on the dispersion and size of the nanoparticles, with optimal performance observed for particles in the nanometer range. Similarly, the addition of montmorillonite clay improves adhesion strength and thermal resistance due to enhanced interfacial interactions between the filler and the polymer matrix. Polyester composites derived from castor oil have also shown promising results. Unsaturated polyester resins modified with castor oil derivatives and reinforced with industrial byproducts such as fly ash exhibit significantly improved mechanical properties. The use of fly ash not only enhances stiffness but also provides an environmentally friendly solution for waste utilization. However, the brittleness associated with such fillers can be mitigated by incorporating modifiers that promote cross-linking and improve toughness. Interpenetrating polymer networks formed by blending castor oil-based polyesters with epoxy resins further enhance damping properties and impact resistance. Polyamide composites based on castor oil are commonly reinforced with natural and synthetic fibers. Microfibrillated cellulose has been used to improve thermal stability and mechanical strength, while carbon and glass fibers provide higher stiffness and elasticity. The choice of reinforcement material and its compatibility with the polymer matrix are critical factors in determining the overall performance of the composite. Epoxy composites derived from castor oil represent a rapidly growing area of research. Interpenetrating networks of polyurethane and epoxy resins reinforced with nanofillers such as montmorillonite or carbon nanotubes exhibit enhanced mechanical strength, thermal stability, and damping properties. Even small amounts of carbon nanotubes can significantly improve energy dissipation through interfacial friction mechanisms. Additionally, shape memory composites incorporating nanotubes demonstrate rapid and controllable recovery under near-infrared irradiation, highlighting their potential for smart materials and biomedical devices. The development of low-viscosity, castor oil-based epoxy diluents further expands their applicability in coatings and structural materials. In summary, castor oil is a highly versatile and renewable feedstock for the synthesis of a wide range of polymers and composites. Its unique chemical structure enables diverse functionalization pathways, leading to materials with tailored properties for specific applications. Polyurethanes, polyesters, polyamides, and epoxies derived from castor oil have already demonstrated significant potential in replacing conventional petroleum-based materials. The integration of fillers and the development of composite systems further enhance their performance, enabling their use in demanding industrial and biomedical applications. Despite these advancements, challenges remain in bridging the performance gap between bio-based and petroleum-based polymers. Continued research is needed to optimize synthesis methods, improve material properties, and reduce production costs. Emerging strategies such as the development of hybrid materials, the incorporation of nanofillers, and the design of dynamic polymer networks are expected to play a crucial role in advancing this field. With ongoing innovation and increasing environmental awareness, castor oil-based polymers and composites are poised to become key contributors to the future of sustainable materials science.